Hey, and welcome to The Explainer. Today we're going to get into something really cool, a blog post that honestly could completely flip how you picture the universe. It basically asks, what if the maps we use in physics, what if they're starting from the wrong place entirely?
So let me just ask you this. When you look up at the night sky, all those stars, right? What are you really seeing? I mean, is that reality as it is right now? Or is it more like a picture painted by light that's maybe traveled for millions of years just to get to you? Yeah, that question, that's really at the heart of what we're talking about today.
All right, so here's how we're going to break this down. First, we'll look at this idea of a God's eye versus our eye view. Then we'll jump into a pretty cool thought experiment with two stars, think about the world through a window, and then, this is the big one, we'll see how the author completely remodels space-time to create a whole new kind of map. It's going to be fun.
Okay, let's dive right in with that first big idea. The core conflict, really. Forever, physics has had this favorite way of mapping out the universe. But our author here argues that this map, it might be showing us the wrong territory altogether.
So this traditional map is what the author calls the God's eye view. And it's exactly what it sounds like. Imagine you have this, a perfect, objective chart of the entire universe. Every single event, past, present, and future, is just laid out on this single absolute grid. It's like a map drawn by someone who's standing outside of space-time, just looking in.
But here's the catch, right? None of us are outside of space-time. We're in it. So the author suggests we should swap that God's eye view for what they call a camera eye view. And this view, it accepts a really simple truth. Everything we can possibly know about the universe comes from the information, from the light that eventually reaches our camera eye. Our entire reality, it's built on that delay. And to make this difference between the two views just, crystal clear, the author uses this fantastic thought experiment. It's all about two stars. It's a really simple story, but it perfectly shows why this camera eye perspective is so important.
Okay, so picture this. You're an observer, floating out in space near the star Betelgeuse. You look out and you see two other stars in the sky. Now from where you are, from your vantage point, the angle between them appears to be 30 degrees. Pretty simple, right? Just like you see in this diagram.
Okay, now let's instantly change our location. We're back here on Earth, and an observer here looks up at those exact same two stars. But from our perspective, the angle between them is now 45 degrees. Same stars, but a totally different apparent arrangement. Weird.
And right there, that creates a paradox, doesn't it? We have two different, totally valid observations, 30 degrees from one place, 45 degrees from another. But in the real universe, the actual physical distance between those stars is a single unchanging fact. There can only be one objective reality. So what gives?
So that just begs the question, if the underlying reality is a single thing, why do our observations of it change so much depending on where we are? Well, this leads us right into the author's next really powerful metaphor. To solve this little puzzle, the author asks us to think about how we actually perceive the world around us. And the thing is, it's not direct. It's always through some kind of medium, kind of like you're looking through a window.
And this illustrates the idea just perfectly. On the left, you've got a real photo of a skylight. It's a window to the world outside, right? Then on the right, we have the author's diagram, which applies that exact same idea to the whole cosmos. The actual stars are way out there in deep space, but what we see is their light projected onto the window of our night sky. So the crucial takeaway here, the big aha moment, is that we have to separate what's real from what we see. Let's break it down. There's G, the real position of the star out in the universe. Then there's W, the window of our sky where its light appears. And finally, P, that's us, the observer's viewpoint. The angles we measure, they're on the window, not in deep space. And that's why they change depending on our position. We aren't seeing reality directly, we're just seeing its projection. Okay, so once we accept this idea, that our reality is built from what our camera eye sees, well then the old maps just don't work anymore. So the author proposes something pretty radical, a complete remodeling of the whole space-time diagram. And look, this isn't just some small adjustment. The author literally calls it a magic remodeling of the classic Minkowski diagram that's used in relativity. Instead of starting from some objective God's eye grid, this new map starts with the only thing we can ever know for sure, ourselves, the observer.
So here's how this crazy idea works. Step 1, you put yourself, the observer, right at the center of the map. Then, and this is the big move, you get rid of the classic X and Y axes for space. Just toss them out. Instead, you replace them with a basically infinite number of axes, all pointing out in every direction. And each axis represents time.
So a point on this new map isn't 100 light years away, it's light that arrived from that direction 100 years ago. See the difference? It's all about time. And here's what you get. This is a map of experience. Distance in space gets completely replaced by distance in time. The universe, from this viewpoint, becomes this giant sphere of past events, and they're all defined by one thing: how long ago their light finally reached you. It's a map built entirely from observation. So, okay, what does a map like this actually mean for physics? Well, it turns out it gives us a completely different way to understand some of its most famous and most mind-bending ideas.
This new perspective completely reframes how we think about things like Einstein's theories. Take the famous Lorentz transformation. The author uses this fantastic analogy. It's not some weird, mysterious force that shrinks rulers and slows down clocks. No, it's just a conversion tool, like translating time zones between, say, London, New York, and Beijing.
So from the author's point of view, the Lorentz transformation is the math that lets the observer out at Betelgeuse and the observer back here on Earth, it lets them translate their different local observations, their different time zones, if you will, and actually agree on the single shared global reality of where those two stars really are. It's not about warping space, it's about reconciling different perspectives.
You know, the ultimate takeaway from all this is it's pretty profound. The reality we experience isn't a direct line to the universe as it is. It's a reconstruction. It's a picture that we assemble in our own minds, using light and information that's often ancient. It's a story told to us by photons that have traveled across the entire cosmos just to get here.
And that leaves us with one final, really mind-bending question to chew on. If our universe, our entire reality, is something that's fundamentally constructed from observation, then what in the world is a universe with no one there to watch it?